We're glad that you're here. Um, and that you have braved the heat to show up. It's nice and air conditioned here. I've often heard Phoenix disparaged as being LA in a microwave. Unfortunately, after so many days of continued heat over 110, I think the correct appliance is a crock pot. So glad you're here. This is the only year I've seen astronomers actually praying for clouds. So hopefully the clouds that we have tonight will be well received and we'll get some moisture out of them soon. Our speaker tonight is via Zoom. He's in Tucson and he sent me his presentation just in case because they are having a storm down there. And so he's got thunder and lightning going in his backyard. So hopefully things are going to work out for us tonight. Why are we not advancing? I just did, and now we do. And now we are. So in terms of welcome, I'm Claude Haynes, the president. Woody is our vice president. He's traveling tonight. James Yoder is our secretary. Treasurer is Brooke Schofield in the far back. Board members, Don Wrigley is actually here because the observatory is closed. Tom is up front. Steve in his lovely red Hawaiian shirt. Alex is at Comic-Con in San Diego. Dave Kosho down front. Okay. And then James is our property director as well. Marty is our webmaster. We're still looking for an events coordinator. We really do need one. So if you are interested, see me. Any visitors tonight? Yes, okay. If you could, yeah, Tom is going to wander around with the mic for our Zoom folks. Now we'll be efficient.
I'm Barbara, and I'm visiting.
Okay, Barbara, where are you visiting from? Ahwatukee, okay, the far reaches of the East Valley. All right.
Mike Orchard, visiting my daughter's family. I'm from Wisconsin, and if you're ever up in the Milwaukee area, we have the Northern Cross Science Foundation just north of Milwaukee, Port Washington area. So I'm looking for a little cooler weather. We're leaving back home, 71 back at home, but cloudy. So I just want to mention a couple things. I was here a couple of years ago, and you guys had a wonderful program on the asteroid Psyche. Yeah, anybody remember? Yeah, and we had a board meeting last night. I attended via Zoom, and it was brought up that it's actually scheduled to launch in October. So that's kind of interesting. It kind of brings back some good memories. And of course, our board talked a little bit about the solar eclipses coming up. So I'm sure you guys are getting ready for that too. We'll have some talk about that. So thanks for having me here. I make it here about twice a year. And
cool.
It's always great to see you guys. Thank you.
All right, great. Thank you.
Yeah,
We're having a fun visit.
Penn, and she was the director of the ASU School of Earth and Space Exploration. And then her project got selected and she had to step down and be principal investigator. So yeah, she's all excited about that, as the rest of us.
I think you've got one more in the back.
I'm Andy, and I'm a professional enthusiast.
Okay, thank you, Andy. We're enthused you're here. All right, anybody else? I think that's it. So tonight, Greco open for public viewing. Friday and Saturday, sunset till 9:30, weather permitting. So that's not tonight. So we are starting that kind of the summer season. So if it's going to be cloudy, let there be rain. But we do look for volunteers. And so if you're interested, please contact me and we'll be glad to talk to you about that. It's really a lot of fun. We actually had a group last night from the Gilbert Rotary Club. They were the ones who built the observatory as a project for the 100th anniversary of Rotary International. That's why we have that big name, big word centennial that nobody ever gets right or figures out. But they were really sweet. I have to say, Don and I did some extra telescopes because we looked at Venus and Mercury and the moon and Mars, and they were really quite low last night. The good news is Don and I were one of the youngest people there. So it was really an interesting group. They were wonderful people. They were really fun. But Rotarians come to retire here in the East Valley. But it was a wonderful group. We had a lot of fun with them. We also have coming up the Explore the Night Sky, which is going to be this Monday. Gordon is doing a presentation. We'll have some viewing afterwards, hopefully if it's not cloudy. But this has been very popular. We had about 50, I think, last time. I think the reservation is pretty much close to that this time. So it's been a very popular partnership with the library. For our presentations this evening, we're going to start now with James Yoder and his second part of filters that he started with last month. I'm going to steal this so you don't.
Thanks, Claude. Okay, so last month, like Claude was saying, we started part one of the filters. We'll do a real quick review of some of the concepts we covered just to refresh your memory, or if you weren't here, to give you an idea of what we're going to talk about. Before we get into that, though, just wanted to provide that link for you at the bottom of the page there. That is the full paper on the filters. It's a 20-page filter. I thought I'd do like a 5-page one, but it turned out to be rather long. So anyway, go to that if you want to see the full details. Last month, we talked about exit pupil, know your pupil size, highest magnification for deep sky objects, and types of deep sky objects. Exit pupil, as hopefully you guys remember, was the cone of light that's coming out of the telescope and going into your eyes. Then we talked about how to calculate the exit pupil for your telescope system. And also, we talked about how to measure your own pupil size if you don't want to go to the doctor, or if you want to find out what the pupil size is at the site you're observing at. This is a method that you can do it using Allen wrenches, and that URL down there tells all about that process. We also talked about the highest useful magnification, trying to get the most details out of your view, but not washing things out by magnifying it too much. And then why these are important, kind of talked about that. Okay, and then we talked about how to make best practices for visual observation, and we'll hit that again at the end of this talk. Okay, so this is what we're going to cover this month. We're going to talk about deep sky objects. You know, what are the different types of deep sky objects? What does a filter do? The types of filters, filters and exit pupils, some filters currently available, and then conclusions. So the topic of this, or the focus of this conversation, let me see if this is going to show. Whoops, did the wrong thing there. Yeah, I don't think the mouse shows. We're focusing on the yellow part down here. You know, there's different types of filters. There's filters used for imaging, filters used for visual observation, and then on the visual part, you know, you can also do planetary filters. We're not concerned with that either. What we're concerned about is the deep sky filters, and that's going to be black body versus discrete, and we'll talk about the details on that later on. So that's what we're talking about tonight. So what is black body versus discrete? This is how I'm classifying the different types of deep sky objects. So things that are very hot, elements that get very hot, like stars, galaxies, globular clusters, and open clusters, all those things burning very hot. The electrons in the atoms are free to roam about. They're not tied to the nucleus so much. And so they emit what's called black body radiation, which means the color of the light coming from them is based on the temperature of the black body. So, and it's a full spectrum, like is on the left-hand side, it's a full spectrum radiation. So those are the types of, that's the type of radiation that is emitted by globular clusters, stars, open clusters, and so forth. Now, the cooler things, like the cool gases like planetary nebulas, emission nebulas, those type of things are very cold, and so they act more like typical atoms do. For instance, when you have neon lights that you look at, they're blue, green, or whatever the color, and that's because those elements are emitting at certain frequencies that are characteristic of that element. Now, most of the gases in in the interstellar medium or in these nebulas and stuff are composed of hydrogen, helium, oxygen, sulfur. Those are the things that are emitting mostly in these nebulas. So what's interesting how they're different from the black body radiation is that they emit at those very discrete wavelengths, as you can see on this graph on the right. So that's a real good advantage when you're using filters. We'll talk about that in a little bit. So the main thing is when you're thinking about what kind of filter you're going to use on an object, you need to know what type of object it is. Is it a black body type of radiation that you're trying to filter for, or is it a discrete type of thing? So let's go on to the next slide. In the good old days when street lights were made with mercury and stuff, the mercury vapor, they emitted discrete wavelengths like the one on the left-hand side. So actually filters were quite good at getting those individual things out. So you could use filters to really clean up sky glow and the city lights. Unfortunately, we're moving off of those and we're almost moved off completely here into LED lighting. And unfortunately, LED lighting, as you can see on the right-hand side, is broad spectrum. So these are very hard to filter out. So that's a challenge. Oops, I don't know what I just did. Here we go. So what do these filters do? What the filters don't do is brighten objects. What they're trying to do is cut the signal of wavelengths of light that you don't want to see, cut that out and not impact the light from the objects you're interested in. So that's what we call increasing the signal to noise, the signal being the light from the object you're interested in, the noise being the background noise. Now, filters can be beneficial for both dark sites and light polluted sites. So what they're doing is increasing contrast is the idea behind filters. So there's different types of filters, and that's because of these different types of objects emitting the light differently. So for instance, a broadband filter on the left-hand side there, the idea of that is to try to cut out street lights and stuff like that, but not cut out the galaxy lights that are coming from the galaxy or globular clusters and so forth. So the ones on the left-hand side, which are broadband, are mostly for black body type of radiation objects. So that's what you'd use there. They're not highly effective. They do help a little bit, but they're fighting, again, they're trying to do this broad spectrum one, which is much more difficult. Now the narrow band ones, which is in the middle here, those are the ones that are looking to get, they cut out most of the light and only let the light in from the hydrogen alpha, hydrogen beta, and oxygen and stuff, so forth like that. So those are the ones that you're going to use on the nebulas, and those actually work quite well. Now, the side effect of those a lot of times is the colors are not true to what you'd normally see in your eye. Of course, for deep sky objects, most of you probably know you don't see colors when you're looking in the telescope anyway. So yeah, I mean, it will could give color, but you don't see color anyway, the most deep sky objects, so it doesn't make any difference. And then there's the line filters, which are filters that are made just to emit or let light through from very individual wavelengths, for instance, oxygen 3. These have very limited uses, but they do have uses occasionally. And typically these will require larger telescopes to use them because they're cutting out so much light. So those are the type of filters. In this chart here, what it does is go across the different conditions and, well, let's start on the left-hand side. The first column is the sky conditions. So the different types of conditions, urban sky versus dark sky, the filter types that you might use in those conditions. And as you can see, we've got the narrow band, broadband, line, and so forth. And then the target types. These are the appropriate targets for those conditions in those filter types. So for instance, if we're under urban sky and we're looking at a black body object like a galaxy and so much like that, you'd use that broadband filter. Now on the right-hand side is the exit pupil range. And the idea of the exit pupil is trying to get the magnification that you're looking through on the telescope to be optimized so you have the best chance of seeing the object that you're looking at. And this is just a starting point. So we'll talk more about this exit pupil. That's actually most of this rest of the talk is about figuring out what eyepieces you want to use to get the best exit pupil. Okay, so what does the exit pupil, when you're looking through telescope, exit pupil really doesn't mean much to you. So what I did was we went and calculated for the exit pupil that was recommended up here on the right-hand side, we go ahead and figure out what eyepieces that is for. Now, each different telescopes has a different focal ratio, and that's what these columns on the 1, 2, 3, 4, the 4 columns on the right are examples of different F ratio telescopes. So for instance, let's take the first row up there. If I'm looking at it, urban sky, and I'm looking at broadband for filter, the pupil range should be 0.5 to 2. But if I have an F10 telescope, that means I should use a eyepiece, start out with an eyepiece of 17 millimeters to 20 millimeters focal length. Okay, so those are the different eyepieces. Now this is based on, as we talked about in the last month, your eye pupil dilation changes as you get older. So this is based for someone who's 60 years old. This chart changes based on your age, and that paper has all the different ages in there, basically grouped down to 10-year increments. So that being said, this is how you'd figure out what kind of filter you want to pick out. So there's a lot of different filters out there. I listed some of them here and try to give you an idea what the prices of those are. I will say this before we get into all the rest of them. That first one there on the road, on the top of the Badier Planetarium, Nebodium, I'm sure I butchered that. It's a sky glow filter, moon and sky glow filter. That filter gets universal good reviews. And the reason why is it's kind of really an all-purpose filter. It doesn't cut light out too much. It kind of crisps up the images a little bit. These are very subtle differences if you guys try them out. It does crisp up the images a little bit, but it hardly cuts out any light at all. And it's really good for looking at planets. It's good for nebula. It's good for broadband. It's good for narrowband. It's generally just a nice little eyepiece to have. The other ones are more specialized. And we've got, like I say, you can see there's a huge difference in price. But what I'll tell you about the first one up there is I just put that in my right angle or my star diagonal, and I leave that in there. And if I add another filter, I'll put it on top because it cuts so little light out. It's a very subtle difference that you don't hardly notice. But I can tell you, I've taken pictures with that filters and compared it to other filters, and it does pretty good. So it may not be really visually astounding to look at, seeing a big difference, but it is subtly helping things out. So anyway, there's a whole list of different filters along with prices there. And now's a good time to go ahead and talk about, introduce you a new program we're starting. We started renting equipment, and so we've now got a new rental program that we have solar filters that you can test. Who wants to go try all these different filters to see which one works best for you? And that's the idea is you really need to test out different ones to see which works for your system because different people have different preferences for filters and will experience different things. So we've got a rental program. You can rent out the filters for $5 a night for the kit or $15 a week. We have 12 different types of filters. We have 4 broadband, 4 narrowband, and 4 line filters. So you can try these different ones on your system. These are 1 1/4 inch eyepiece filters. We also included on the kit a filter wheel. This does work for Schmidt Cassegrains. It may not work for some of the other ones because of the focal range. The nice thing about this, if you put the filters in here, you can just dial in different filters and compare them very easily as opposed to taking the eyepiece, putting the filter on, putting it in, and then getting another filter. So this one, you can actually just dial and check them out. So it's kind of nice. We also include a little bulb and cleaning brush. So that's introduction to the filter rental program. And like I said, there's some of the filters. And let's just go ahead real quick and review what are some good practices in general when you're trying to observe at night is make sure you give your eyes 30 minutes to get fully adjusted to the dark. Make sure you pick a dark site. That's really important. The darker the site, the better. Optimize your equipment. Make sure it's collimated and got clean optics. Use a diverted vision when you're looking at things, especially dim things. Averted vision is when you don't look at it directly, you look at it off to the side of the eye because, and I always get these confused, the rods are on the edge of the eye, I think, right? Yeah, so those are more sensitive to light. They don't see color, but they're more sensitive to light. The cones are in the middle of your eye and they are not as sensitive to light. So that's why if you don't look at it directly, you'll see more details. Magnification, start with appropriate magnification that we talked about some last month. And then increase the magnification to the backgrounds fairly dark. Some manufacturers recommend you get it to it's black, but I prefer just seeing a little bit of the background so you can see you're looking in the eyepiece. And then take time when you find the object to enjoy it and let the atmosphere play out, and you'll get some moments of good crisp views on there. And also use a proper filter based on the discussion we had. If you're looking for planetary nebulas, these are small little items that almost look like stars. One method that the people use is taking a filter and just sliding in front of the eyepiece. And if one of the star stays and all the other one goes, that's a planetary nebula. So that's that. Conclusions. Don't expect too much from filters. These are very subtle. As I mentioned, the Bay-Deer Moon and Sky Glow is a great little starter to have, and prioritize your purchases. Personally, if I were to have to go buy stuff, I'd first get the Bay-Deer, then I'd go to narrow band because you're going to get most impact from the nebulous type of filters, and then the broadband. Try it before you buy it. Try it out here and see what you like, and then go out and buy what you want. Again, want to thank both Toms for helping me with this presentation, and my wife, Laura. Any questions? Question? One second. Sure. You wanted to see the main URL, right? Okay. Did you have a question with that or anything else? Yeah, it's just tinyurl.com visual filters -2023. Right. Okay, okay, so the question is the difference between visual versus astrophotography filters. And the main thing about the difference on this, the visual is we've got a very narrow set of wavelengths that we can see. With the cameras, they can see in the infrared more. So the filters are different. A lot of times, I mean, yeah, so when I do a lot of astrophotography, the ones I would use for visual, I probably don't use for astrophotography. Although that Bay-Deer does pretty dang good by itself, which really surprises me because it's just an all general purpose filter. So yeah, there is a difference, and mostly because like the hydrogen alpha is again a pretty high emitting thing, but we're not as sensitive to that as cameras are. So there's a difference between the two. Yeah. Like the HA generally isn't used for visual, but the hydrogen beta is used for it. And the bandwidths on those, well, you see, I don't want to spend too much time. When I do my imaging, I'll go straight to what's called a radian, and it only has 3 wavelengths that it lets through. That's for the nebula. Now the broadband, I have to use another filter, but that's only letting 3. I wouldn't see hardly anything with my naked eye with that thing. Because it's just cutting everything else out. So, yep. Okay, thank you.
Thank you, James. We appreciate all the hard work on that. For our speaker, Matt, I'm going to stop sharing and you can start getting things together as I do a very brief introduction for our speaker tonight. Dr. Matt Penn His parents brought him a telescope at age 8, which is about the appropriate age for telescopes, and he was hooked on astronomy. He got into solar physics during his undergraduate work at Caltech and researched oscillations in sunspots for his PhD at the University of Hawaii, which is a nice place to go to school if you're going. I joined the National Solar Observatory rather in 1992, but then took a 3-year vacation to teach physics and astronomy on the faculty of Cal State Northridge in the 90s. He then worked with the National Solar Observatory through 2018, and then kind of left the NSO to stay with his family in Tucson. He's currently an electro-optics engineer at Raytheon and also an adjunct faculty member at Southern Illinois University, Carbondale. So he's pursuing astronomy as a hobby now, and he's very happy to work with all sorts of wonderful amateurs as well. So what I'm going to do is let me move my screen, if I can. Okay, guys, why is it not letting me zoom? Exit full screen, thank you. And there we go. And so, all right, Matt, thank you for coming and speaking with us tonight. You're in Tucson, so he is actually experiencing monsoon weather. So if we have any interruption, he sent me a PDF of his file so we can kind of react to that. But I think we're all set. Take it away.
Excellent. So you can see my title page then?
Yes, sir.
Okay, thank you. Thank you for the invitation. And yeah, I'm trying my best to send these monsoon rains up to you guys. I'd like to actually take some data sometime, but might not do that for the next 2 months. So I'd like to talk to you today about the Eclipse project that we have going called the Dynamic Eclipse Broadcast Initiative. These are just a couple of the people who are working on the project. So we've got a core group of about 20 at this point, and then we have many volunteers coming through the project as well. And as was mentioned, I'm an engineer at Raytheon, amateur astronomer, and adjunct faculty at SIU Carbondale. So here's my Gmail address in case there are questions that I don't get to, but please interrupt or put a comment in the chat. Okay, so first I'd like to go over what kind of science can we do from the ground during an eclipse, and what did we do in 2017, then review the project sort of management that we did in 2017, and then tell you what we're going to improve for 2024 and offer opportunities for you to get involved. So as you know, a solar eclipse allows us to see the corona, the hot atmosphere of the sun. And from the ground, we can use special telescopes called coronagraphs to do this. But a coronagraph is sort of like the figure on the left, where we're blocking out the bright disk of the sun. It's not quite as simple as this. There are other stops in the telescope. But what happens is that sunlight scatters off of dust particles in the atmosphere, or molecules of nitrogen, and we can see a background illumination that prevents us from seeing the coronal structures. The corona is about 1 million times fainter than the disk of the sun. So from the ground, using specialized coronagraphs, we get this scatter, and we have a much lower signal to noise ratio than during a total solar eclipse, which is on the right. The moon obviously is a much bigger object, and more importantly, the shadow of the moon blocks the atmosphere around the observer. So there's no atmospheric scattering. So we're able to see the corona much more easily and get higher signal to noise ratio in our images of the structures. The sky is about 10,000 times darker during an eclipse than it is in the best coronagraphs from the ground. So that's why it's advantageous to observe the corona during an eclipse, but everyone knows that NASA has several missions in space looking at the corona. What can we do from the ground that is different? Well, as James mentioned, the sun is mostly a continuum emitter. And if we look at the corona in broadband wavelengths in white light, we can see all of the temperatures of the plasma in the corona. The coronal plasmas range from about 50,000 Kelvin up to even 100 million Kelvin. So there's a wide range of temperatures. But when NASA looks at the disk of the sun using filters from the SDO spacecraft, they're limited to narrowband wavelength filters, as James was talking about. So it can only pick out particular temperatures of emission. So we can see these particular temperatures on the disk of the sun and a little way above the limb. But we were not seeing the entire corona, all of the plasma that's there. NASA also has a set of coronagraphs in space, and LASCO C2 is the one that currently gives us the closest view to the limb of the sun. And this does show us white light. So it does show us all of the plasma along our line of sight. It's because the solar illumination is scattered off of electrons, it's a process called Thomson scattering. And the continuum that we see then maps out all temperatures, and it's sensitive mostly to density. So regions that are dark are lower density plasma, regions that are brighter or where the plasma is higher density, independent of temperature. This really allows us to track features as they move out through the corona. But unfortunately, NASA's LASCO field of view doesn't go down to the limb of the sun. And so inserted in here is a picture from our 2016 Eclipse experiment, and it fills in this gap. So what we're looking at doing, in particular for 2024, is also matching the really close-in imaging that's done with SDO with the LASCO field of view out at 2.2 radii or higher. So I'm not sure if it's a coincidence or not, but there's a lot of reasons to study the inner corona in white light. A lot of the physics that's still unknown about the corona is hiding in that region. So if I really make a simplification, when we're looking at the solar wind or looking at eruptions coming off of the solar surface, by the time they get into the LASCO field of view, they're moving at a constant speed. So it's as if you're looking at cars moving on I-10 and they're all moving at 75 miles per hour or 85 really. But we don't see them accelerate. At the surface of the sun, we don't see any blue shifts. So we know the plasma is stationary there. And we know that in that region between zero or between the surface and the LASCO field of view, these particles accelerate. So our Eclipse data is basically allowing us to see the on-ramp on I-10, where a car is moving at 0 speed at the top of the on-ramp and then accelerates up to 85 to match the velocity in the solar wind or on I-10. So why do we want to do that? Well, by measuring acceleration, we're getting clues about the physical processes going on with these particles. Just like if you're accelerating onto I-10 in an electric vehicle, you can floor it and go from 0 to 85 much faster than you can in a 1970s Camaro, for instance. So understanding the acceleration and how these particles go from 0 to the solar wind speed reveals important physics. And it's something that we can only study by looking at the inner corona. And currently, a solar eclipse is the best way to do that. So in 2017, we set up the Citizen Continental America Telescopic Eclipse Experiment, or Citizen CATE experiment, where we had 70 sites across the country from Oregon to South Carolina. And this was like a relay race. So when the lunar shadow uncovered our first site in Oregon, it had already covered up the second site, and so on. So the sequence of telescopes across the United States imaged the corona, and we obtained about 90 minutes of continuous data. The reason that we have to do this is, even though the velocities are fast, we're talking about hundreds of kilometers per second. The corona is also very big. And so during a total solar eclipse at one location where you only have about 2 minutes, you can't really see a lot of motion from one site. But by stitching together data from 70 sites, we're able to get a lot of the transverse motion of the plasma and measure accelerations and velocities. So let me show you a sample image. This is combined data from one of our sites of the 17 eclipse. And there are a lot of different features. There's some close-in surges and of course, in their limb. We also saw a couple of stars in our field of view. But our main focus was some outflowing material that was the remnant of a coronal mass ejection that happened just before the eclipse occurred. And so we focused our efforts to measure velocities of plasma blobs or plasma packets in this part of our field. And so we were able to publish our data in a paper in 2020. This was myself and 287 of our volunteers as co-authors. And what we measured was the radial velocity, the outflow velocity of particles here. So in the LASCO field of view, up at higher elevations above the limb of the sun, LASCO was seeing a constant outflow of about 250 kilometers per second for this CME. But then in our field of view, closer to the limb of the sun, we saw much lower velocities, and in one case, something that was pretty high with big error bars. But, you know, as in a lot of science, it didn't fit any really clean, easy theories. If the coronal plasma had an extra acceleration above the solar gravity of 15 meters per second squared, then all of our data points would follow this dotted line. And clearly they don't. You could drum up some other reasons for why they might fit a linear acceleration curve, but they don't do that either. So we see a really complicated acceleration process going on through the inner corona for this event. This is the first measurement in white light ever done. And so the bottom line is that for 2024, for the next total solar eclipse, we'd like to make the same measurement and hopefully have some outflows, probably several of them, because it'll be an active period in the sunspot cycle, and understand if this is a unique acceleration profile or if other events show different speeds, different accelerations. All right, so how did we get this project going, and what are we going to improve on it for this next round? So back in 2017, we had practiced a little bit. I should say, well before this, I got this idea from a French colleague of mine, Serge Kuchmy, who set up a network in 1999 in Europe. Unfortunately, he wasn't able to publish much of the results. But the idea of having a string of telescopes along the path of totality is something that's been done or attempted several times. We wanted to try it again in the US. So we had a practice run in 2015, about just over 2 years ahead. And then in Indonesia, another eclipse in 2016, a year and a half. And then of course, 2017 was T=0 showtime. For our practice run in 2015, we got pretty lucky in that Fred Isbener, alumni from Southern Illinois University, Carbondale, told us that he was going to the Faroe Islands. And if we shipped him some telescopes, he'd be willing to try to take some data for us. So Fred had never done any astroimaging before. He was new to the idea. He had some telescopes and did some visual work, but never taken any pictures. So in the winter in Illinois, we trained him on the 2 clear days. And we shipped the telescopes to his hotel in the Faroe Islands. It rained on the morning of the eclipse, and you can see clouds. Conditions were terrible. But nonetheless, Fred was able to come back with an image of the corona. So here's an image taken with one of our prototype cameras showing coronal loops and darker areas in the poles and some bright prominences along the limb. So this serves as proof of concept that we could work with somebody who actually wasn't into astroimaging at all and train them. And actually, Fred performed magnificently in terrible weather under very tight time constraints and came back with some images. Our second attempt, practice run, was in Indonesia, where now we had some NASA funding, so we were able to send 4 groups to the islands, a faculty member and an undergraduate student from each of our 4 universities, Carbondale, Wyoming, Western Kentucky, and South Carolina State. And Indonesia had terrible weather as was forecast, but one of our sites was able to collect data. And here's a highly filtered image of the corona that was obtained from that site. We actually had a time sequence from that location. So we didn't really achieve our goal of making a network of observations in Indonesia, but we were able to train several groups of faculty and students to successfully take data, assuming the weather conditions were favorable. So the other thing was that we didn't just give these students a free vacation. Since they were now trained and had on-the-job experience, we made them or volunteered them to help train the volunteers for 2017, a much bigger group. And they acted as coordinators along with several people in different states where the Eclipse path crossed. So, I know nothing about good observing sites in Oregon. So the best idea was to get a local person, Mike Conley in this case, to tell us that we should observe at different locations than we had planned out. And he also identified volunteers who were willing to take the data. And we did that across the path of totality. So along with our students from Indonesia, these volunteers were our state coordinators for 2017. And for that project, we had a large set of groups involved. We had input from 27 different universities across the nation, 22 different high schools, and actually one middle school student as well. Some museums and informal science education and some national labs participated as also. We had them all attend in person a training session in their home state or in their state of observation. And that's where we distributed the equipment to them and trained them over a day and a half how to use it and how to use our software packages. The goal, one of the goals of this project was that the groups would keep the equipment after the eclipse, and we were able to achieve that. So everyone picked up their equipment at these training sessions, brought it home and practiced for the eclipse. And several of them have been using it after the eclipse for follow-up studies or outreach. So during the day of the eclipse, things were pretty exciting. We had 70 locations, as I said, 117 students involved, both at undergraduate and high school level. And as you know, the conditions were very favorable on that day. We had a wide variety of sites from mountains in Oregon to, a lonely farmer's field in Nebraska, sort of a suburban location in South Carolina. And then at some of our locations, we had really high pressure environments where tens of thousands of people were in a stadium at the university here in Carbondale, but also at Tennessee Tech and other schools. And so our observers were frantically trying to concentrate and collect data while everyone was screaming in the stands. But we got some great results, and as I showed you, we published a science paper from our efforts. In terms of follow-up science, we had a couple of papers published, one looking at the ellipticity of the corona. And then Zach Stockbridge published in The Reflector a sort of a traditional calculation of the astronomical unit. Transit of Mercury occurred after the eclipse, and several of the volunteer groups observed it across the country. And using the baseline between different sites, you can find parallax on Mercury or on the image of Mercury and calculate the astronomical unit. A couple of our advanced volunteers actually observed exoplanet transits. It was a small 80mm telescope, but the error bars were small enough and the number of data points collected were fast enough so that we were able to clearly see an exoplanet transit. And Rob Zellum from JPL published this along with other small telescope observations of exoplanets back in 2020. And then many of the students that were involved in our project entered their ideas into science fairs. And I worked with a couple here in Tucson. We had, 4 or 6 students win some, some substantial prizes. So we're hoping to do similar follow-ups with 2024. Actually, we have a better plan to execute those now. Okay, so even though we felt it was a pretty successful event in 2017, there's a lot of room for improvement. So one of the things that I was hoping to do in 17 was to broadcast the event that night. If you look at the public interest in an eclipse, it peaks on the day of the eclipse, and about 2 days later, nobody can remember that there was a solar eclipse. So having something showing the coronal evolution that night would be very important. So we've worked into the name of our project this time, Dynamic Eclipse Broadcast Initiative. We'd like to broadcast our data in real time or almost real time the day of the event so people can see those results. We want to make it cheaper to get the equipment, and we're successfully able to do this. We're using some standard off-the-shelf components this time. An ASCAR small telescope, you probably are familiar with it, a small camera from Player One, and a nice go-to mount from Skyhunter, a small, portable, inexpensive mount. We'd also like to have participation outside the path of totality. So the science isn't going to really be a big bonus. We're not going to get a lot of added science from them, but we will be able to see disk activity that may correlate with coronal ejections. But also it'll be a much better broadcast if we can show the partial eclipse to people who can't travel to the path of totality. And finally, we'd like to make it easier to do the follow-up work at night. The Skyhunter mount is a go-to system, and that was one of the limitations with our previous system, is that it was hard to point it at night. So we got a pretty good head start, but we don't quite have the opportunities to practice like we did for 17. We've had 2 total solar eclipses, and the other one was in Antarctica. And we've made efforts to do some tests here, and I'll show you the results. But we've also been using lunar eclipses, and we've had several of those in the past year and a half. So here is the annular eclipse coming up in October, and we're going to be collecting data for that. It won't be quite the same, won't be like a complete dry test for the total eclipse, but we'll have some test of the equipment and preparation, see how the training has gone. And then of course, April 24 is the showtime for this one. So back in November of 21, we were able to observe the lunar eclipse from 3 sites, although Tucson was pretty cloudy that night. And here we have 2 images taken at the same time, one from Tehachapi, California in the blue, and there was some cirrus. You can see some light blue background. And then in the red from Greenville, Texas, just outside of Dallas. With a proper pair of 3D glasses, you can see the moon pop out from the background stars. And so we're able to test out our real-time data upload, if you will, during this event too. We only had about 5 people observing or online, and we were able to see each other's images at the same time. In one of the more recent event eclipses, so this is November of 2008, we really, the previous images were taken with a Raspberry Pi camera. We were hoping to use Raspberry Pis at the beginning of the project, but they have gone extinct. It's hard to find them now. So we've now switched in this eclipse to the Player One camera, and it gives us 2 more bits. It's a 12-bit camera rather than a 10-bit camera. So we're able to do a high dynamic range image a lot more clean than with the Pi camera. And so during this eclipse, we were trying to map out changes during totality. So here's a strange sort of composite image of the moon with false color. I've kept the background stars fixed and just added in the lunar image during the 2 hours of totality. And this is supposed to sort of match up with the Fred Espenak's diagram here in Sky Telescope. But what we're looking for here is sort of asymmetries in the shadow of the Earth. A lot of the textbooks show the shadow as being nice and symmetric and circular. But if you think about it, during a lunar eclipse, the moon is red because of light that's refracted around the limb of the Earth. And during the course of 2 hours, the Earth is rotating a significant amount. So the cloud structure and the atmosphere that that light is propagating through changes. And so you'd expect some changes in the shadow. And you can sort of see it here in this color image, but it's much more clear in the gray scale down here in the lower left. We see some strange rays and other types of structure in the Earth shadow. So again, as kind of a sort of exploratory project based on this lunar eclipse data that we're able to collect with our system. Now to get to the solar eclipse results. So again, Fred Espenek, he's a world traveler. I'm sorry, Fred Isbener is a world traveler. He told us that he was going on a cruise with his wife to Antarctica. So we said, gee, how about if we ship you a telescope? So in the intervening 5 years, a telescope package has significantly shrunk. So here we have a Raspberry Pi with just a 50 millimeter lens, I think, on it. So Fred was able to get on a cruise, and if you remember the story that happened in December of 21, there were about 7 cruise ships in the South Atlantic, and only one of them actually saw the eclipse. And the good news is that was Fred Isbener's cruise ship. They saw the eclipse. The bad news is that right before totality, the captain had to reverse course and chase this hole in the clouds, and Fred was set up on the wrong side of the ship, had to take the equipment down and move it to the other side, and didn't get a picture of the corona. He did get a picture of the partial phase, and you can see the amazing job the captain did. Here's the ocean, is this bottom dark line, and the cloud deck here. So there's about 1.5 degrees of space that he was able to position the sun in. So that's quite some navigation. But unfortunately, we didn't get any coronal images. Since we've moved on from the Raspberry Pi, it's not such a huge loss. And then last April, there was an eclipse visible. The total solar eclipse path just barely nicked the northwest corner of Australia. And so SIU Carbondale sent a team, actually a couple of teams of students down to Exmouth on that northwest corner. Some of them did outreach. So here we see a bunch of the local Australians interacting with the students in the maroon t-shirts. On their trip up the coast of Western Australia, they took many nighttime images of southern objects. And then during the partial phase, they were able to collect an image of the partial eclipse through our DEB instrument. And so here you see some nice sunspots and some detail along the lunar limb. But unfortunately, and actually they're really well, halfway through the eclipse. And unfortunately, the eclipse was only about 60 seconds in duration, so there wasn't much time to adjust. So we didn't get any coronal images with our DEB instrumentation. They did bring along a backup telescope with a much smaller field of view. And so we do have some data from that telescope. The camera is sort of a test camera. The prominences are well overexposed, as you can see here, but we're able to see some structures in the inner corona. But unfortunately, we don't have detailed information or images from the DEB instrument. Now we're going to do some tests with this backup telescope and bootstrap our way to the DEB instrument. And the goal here in Australia was to refine our exposure times. So we'll have the intensity information to do that. But as you can imagine, the team was sort of disheartened after traveling to Australia and then bumping the telescope at the last minute. But this is the kind of thing that happens during an eclipse. It's really a challenging project. Okay, so for 2024, we've settled on an equipment list. And again, we're using the ASCAR FMA 180 Pro. Some spacers, the Neptune camera, the Skyhunter mount. So the bottom line is that this whole package costs about $1,700. It's about half the price of the 2017 package. And it gives us 12 bits rather than 10, and it gives us a wider field of view and a faster system than we used in 17. Some of the example laptops here, a lot of our volunteers already have laptops that fit this range. And so we'll be able to spread our budget a lot easier. We were recently selected for funding from NASA and from the National Science Foundation. So we'll be able to provide instruments for our volunteers again. Here's what the setup looks like in my backyard. This is a tiny mini laptop from GPD. So don't think that's a full-scale laptop. But the aperture is 40 millimeters across. And the Skyhunter mount, again, is a very portable, and I've loved this mount. I actually tried to kill one. I put it on my rooftop in Tucson at the beginning of, or the end of June, before monsoon started, and took about 4 days of data when it was 115 degrees, and it didn't melt. It tracked, it did meridian flips for 4 days straight. So I like this mount a lot. Some of the imaging that we've been able to do, here's a solar disk image, shows about the same detail as the partial eclipse. What we're doing is using a program called Planetary System Stacker that will stack images, sort of like Deep Sky Stacker, but it also has a wavelet filtering system built into it. And more importantly, it can be called from a command line on a Windows machine. So the idea that we have now is to use SharpCap Pro and a script in SharpCap to take the data and also call the Planetary System Stacker reduction, and then upload it to a cloud drive from there. I think this system is going to be really good for our volunteers too, because it's a good starter system for astrophotography if they want to get involved. So here's some astrophotographs that I did for my backyard. Here's the supernova M101. There was that nebula, obviously, last winter, M8 with no stars. And I was experimenting, and the horse head. And then if our volunteers want to, upgrade and buy different cameras or different filters, I think the ASCARs and the Skyhunter are good systems. Here's the sun with an Antlia calcium K Herschel wedge, $400. So you can see a lot more structure on the disk of the sun just by adding this to the system that we have. And then, of course, the Rho Ophiuchi dark nebula cluster gas cloud. This is using a different Player One camera. So it's about a $800 upgrade to our system. Nice wide field, deep sky imaging. But besides astrophotography, we've got some specific science follow-up projects that we'd like people to work on. Of course, exoplanet observations are something that Rob Zellum in particular is interested in getting our teams to look at, and more people can do this with our go-to mount. They can find HD 189733. But we've also looked at some asteroid light curves. So here's Cleopatra, taken over the course of 6 nights, I think, lined up in phase. Jeff Wise took this data from California. And we're interested in doing some solar work as well. So one project is to look at the sun as the solar cycle ramps up and measure white light flares. We're able to get about 60 frames per second out of this camera on most of the PCs that we've tested. And no one's observed white light flares at that sort of cadence. Now, it's hard to predict a flare, and a white light flare is the most energetic type of flare, so it's almost impossible to predict them. So having a network of several sites across the country that can observe will help us out with that. And then, from our backyard, we were able to look at oscillations on the surface of the sun. These are things I did my graduate work on. These are waves, acoustic waves that travel through the solar interior and follow a pattern of the wavelength or angular degree and the temporal frequency. Their power peaks out at around 5 minutes of time. So with our new setup, and particular with the go-to mount, we're hoping that these follow-up projects will have more participation than in 2017. As I mentioned, we've got some funding currently from the National Science Foundation. We're partnering with a film, an IMAX film called Einstein's Incredible Universe. And they're going to fund 20 sites across the path of totality. We just got a grant from NASA for heliophysics citizen science that'll fund 40 sites. And then people on our core team have been very generous with purchasing equipment and making donations. So we've got about 10 sites or maybe a little more from that group. And currently we have about 40 volunteers. I'll show you a map of the path of totality. What we need now is particularly funding for our international sites. We can't use federal funding for those equipment packages, and some volunteers that might want to travel, or if you know people who might want to travel to those areas, Mexico and Canada, but also in the Northeast United States, we have some gaps. I'll show you a map again. So we're looking for site volunteers and people who might be more interested in being coordinators of several teams. So like I mentioned, we'll practice on the annular eclipse coming up in October. We'll have several sites along the path of totality. There's not a lot of science to do here, but there's an interesting demo, I think. The Bailey's beads during an annular eclipse and also during a total eclipse are caused when the sun shines through valleys or is blocked by mountains on the lunar limb. Now, if you're looking at the moon from Oregon and in Texas, not only does it appear in different parts of the sky, but you see slightly different limbs. And so we're going to try to look at how the Bailey's beads vary across our path, across the people that are in the path of the annular eclipse. And hopefully it'll make an interesting movie. For the main event in April of 2024, let me see if I can bring up our map. So here's, let me show you this one. Here's a map showing the optimal spacing between sites. If we wanted to do a relay race again across the path totality, we'd start in Mazatlan and then go up to Newfoundland. And these are the volunteers that we currently have, some of them outside of the path and also many in the path. We've got about half of Mexico covered. We need some more volunteers here in the northern part of Mexico. There are too many volunteers in Texas, but having overlapping coverage might not be a bad thing. If you remember, I mean, the overall climatic forecast is for the best weather in Mexico and Texas. But if you remember last April 8th, Mexico and Texas were clouded and the rest of the path was completely clear. So we'll see how that maps out next year. Our coverage is pretty good through the middle of the country. Up around New England, Ohio, and New York, we're missing a couple of volunteers. So we'd love to get people who are interested in traveling there or already live there involved. And then, of course, in Canada, we've just got a couple of sites here. Again, Newfoundland has some chance of seeing the eclipse, and the weather won't be hot, that's for sure, in April. So we're hoping to get volunteers there as well. Okay, so I'd like to end and start to get questions with the slide about how you can volunteer. Again, our core team, we've developed a hardware now, but we're working on the software. And if people are interested in developing curriculum to help either at the high school or the university level, that would be a fantastic thing that we don't have currently filled. And finally, public outreach. Each of our sites in 2017 was the nucleus of quite a large event. I went to Weiser, Idaho, a town of like 3,000, and they ran a huge event with 20,000 people on the day of the eclipse, centered around the high school where the Kate team was. Again, regional coordinators, these are people who are more involved and work with several groups rather than just one, but we're also interested in site observers, people who would go with a group of 2 or up to a dozen to a particular location and take data. Again, if you're interested, here's my Gmail. Our group has a general Gmail account as well. And then our website is devinitiative.org, where we have some introductory material and some YouTube videos. And that's all I have. So be happy to answer questions.
Okay, that was on you. All right. Do we have any questions in the room? Okay, I think we don't have, Tom? He-
Have Matt see it. There is a Zoom one. You can see the Zoom Q&A.
Oh, okay. So Matt, you can look at the Zoom Q&A if you see anything there, or
Oh yeah.
there's one there, I think.
Oh yeah. Lots of comments. Thank you. Let's see. Photography, auto
Hey, Matt,
stacker.
just look at the Q&A. Ignore the chat.
Okay. Not so sure I can get to that.
I can read them for you if you want.
Yes, read it.
Here we go. Sorry. Okay, I've got there. We plan to view the October and the April 2024. So for the October annular, I'll be going to Hobbs, New Mexico. There's a small college there called New Mexico Junior College, I think. And we'll establish a site there for the annular. It's pretty close to dead center on that path. And they'll also observe, there'll be one of the out of path observation sites for 2024. And for April 2024, the most compelling place to go is Uvalde, Texas. They've had some bad things happen in that community. So I saw they're on the path and decided to go. So I'll be working with a teacher and their students there. But, given my luck, maybe that means it'll be cloudy. Let's see, do you use plate solving and sharp cap? Yes, so plate solving and sharp cap is particularly useful for doing polar alignment of our telescopes. We've got some devices that we're working on to do daytime polar alignment, but the hope is that people can set up the night before, and the sharp cap polar line is really a great tool. I use it all the time, which involves plate solving for that. Of course, during the day, it's not helpful. Texas is filled. Yes. Again, having overlapping coverage is usually a good thing. So please send me an email, and we'll see. We may not be able to purchase equipment for everybody in Texas. We've got our sites sort of filled out already for that. But if you'd like to volunteer, yeah, send me an email and I'll get you involved in the group. All right. Sorry, Elko, Nevada. Yeah, actually in Elko, we have one of our core team is working with a school in Elko, Nevada for the annular eclipse. So George, if you want to send me a note, I can connect you with, I think it's Jeff Weiss, who made the asteroid observations, and let you know if you want to get involved with the school group there for the annular. And then Killeen for the total is again one of our very popular Texas locations.
Hi, Matt, this is Bob Buckheim, you may remember from SAS.
Yes.
You asked for funding and volunteers for Mexican sites. Could you elaborate a little on that? I might be in Torreon.
Oh, well, yeah, excellent. So we have 6 ideal locations mapped out for Mexico, and we have some along the coast, but not a lot towards the Texas border. I'm not sure where Torreon is. Is it closer to the coast, or I guess I could Google.
It's about midway.
Midway. Okay. Well, it'd be fantastic if you were there. The difficulty that we have with supplying equipment is that we can't supply equipment to foreign schools. So we have a special private pot of money. I've been donating, and some of our core team has donated money as well. And so we can buy equipment for local Mexican groups that way from that pot of money. So if you wanted to partner with
Price
a
for the setup. What's the total price that we're talking about for the setup?
the total is about 1,700 without, if you had your own mount and your own laptop, then it drops down to, oh gosh, 800 or so. So I know one person is going to, I'm sorry.
That's not a problem.
Okay, excellent. Well, then please send me an email. I would love to talk to you and get more details. We're missing people for the coverage in Mexico.
Any other questions here in the room or from Zoom? If not, Matt, we really appreciate it. It's been a fascinating presentation. Good luck with finding all of the people and all of the logistics. That's a lot of details. So we really appreciate you planning this out and thinking through all of the contingencies. The last thing you can do is plan on the weather, but you can work for everything else.
Yes, in 17, we had scientific data from 50 of our 70 sites. I'm not sure we can hope for that this time around, but we'll take what we get. And thank you again for the invitation. And I'm looking forward to talking to you, the folks in your audience who have questions or further comments.
All right, thank you very much. We appreciate it. Thank you. Here. To get rid of that view. Exit full screen. That must be screen 2. We'll figure out how this works in a minute. And I should be back to my settings. I'm not sure where we are. Share. There we go. So. We have all of James. There we go. So basically, thank you. We appreciate it. We'll see you next month. You don't have to do taking away of chairs. There's a wedding here. This is such a romantic location for a wedding, but they have a wedding scheduled tomorrow. So we don't have to take down the chairs, but we do need to take down the tables. Thank you very much. We will see you again soon. Stay safe, stay hydrated, and stay cool. Good night.